So next up is another member of my lab, a research scientist at the Brain and Mind Institute in Western. This is Bobby Stojanoski. Bobby did his PhD at University of Toronto, and then he came to Western to work originally with Rodri Cusack on imaging neonates, very, very young babies, who of course have dubious levels of consciousness at the best of times. And he worked for a few years with Rodri, and then he switched over to my lab, bringing some of the techniques that they had been developing in the baby imaging to sort of combine with some of the things that we have been doing in the patients, because methodologically there are actually many similarities between trying to image those two populations. Bobby, as I said, has been supervising Jeff, and he's going to talk today about sleep, about some studies that we've been doing using some of the same kinds of techniques, using EEG to sort of decode states of awareness induced by sleep.
Thank you, and thank you for having me here. I look forward to chatting with as many of you as possible about the exciting potential of decoding mental states and thoughts using EEG. I'm going to move away, as Adrian pointed out, from assessing the presence of, is that better? Of consciousness in patients with disorders of consciousness, and instead focus on the degree to which there's shared conscious experiences in a different state of consciousness, and that is different stages of sleep. Having said that, you will see common themes throughout this line of work, and I'm grateful that Jeff fielded most of the difficult questions about the methodology. And so, and because he went into some detail about that, I'll only talk about it very briefly, but again, I'm happy to discuss that in more detail. So, turning to sleep, this has been a fascinating puzzle for scientists, neuroscientists, and philosophers for as long as these fields have been active. There's always this idea that sleep is this period where our brains are open for business. That we, once we've shut down from processing the nuances and complexities of our real world, we lay down, and then our brains are ready to do whatever we want them to do. And so there's ideas that you could learn anything in sleep. So simple things like tapping your fingers, which will eventually make you a concert pianist. You could learn. You could read books in your sleep, and even learn new languages. Of course, these ideas have been debunked, but the questions remain whether, if any information it is being processed at different stages of sleep. And the answer seems to be yes, and quite a bit. So there's been early work on processing an auditory P3, so when there's a surprise event in a series of regular tones, your brain is picking this up at different stages of sleep. You can associate odors with auditory stimuli, specifically in non-REM sleep. So some recent work has shown that your memories for fairly simple auditory stimuli get strengthened during REM sleep and actually become suppressed in other stages of sleep, in shallower levels of sleep like N2 and N3. Some recent work by Shrivas actually has shown that what happens when you transition from a period of wakefulness to sleep, it's not that your brain shuts off, it's that your brain is a much more flexible system, and you get changes in frontal activity, and you get changes in alpha and theta as you go from being awake to sleep state where you can no longer respond. But it's not only limited to really simple stimuli. Some work by Sid Cudier and Tristan, a former postdoc of Adrian's, has shown that you get semantic level processing as you doze off into sleep. So in this task, they used the lateralized readiness potential, so that is activity associated with your willingness or your readiness to respond to a task. And even as you doze off into sleep, your brain is producing this signal even though you can't respond because you're falling asleep. So this work, so a lot of this early work is focused on relatively simple stimuli. Of course, it's going to be auditory by the nature of the fact that you don't see anything when you're sleeping. And most of the work is focused on the transition from wake to sleep. And to date, very little has been done on how much whether or not we're able to process rich information when we're already in a certain level of sleep. And so, so the talk is on decoding our mental state while we're in sleep. And so I won't spend too much time discussing the details of sleep, but I will go over it very briefly because this is relevant for the data that I'll present to you. And so I think all that you need to know now is that as you move from stage 1 to REM, you transition to a deeper state of sleep. So at stage 1, you're drowsy, you're picking up some information, and whereas REM, the idea is that you're not. And each one of these stages is associated with a characteristic electrophysiological pattern of activity, which can be used by people to identify which state of sleep you're in. So looking at K complexes and spindles and things like that. So I'll tell you about what we did. So this project, so what I'm going to present to you, the work I'm going to show you here is part of a larger project that looked at not only movie processing and EEG in sleep. Of course, that's what I'm going to focus on, but we also, the data that we record was from participants who were in the scanner, who were falling asleep in the scanner. And so we got structural data from these participants. We gave them 8 minutes of rest, and then we let them sleep for 90 minutes. At the end of that 90-minute period, we played them a 5-minute clip, the same taking clip that Jeff talked about earlier. And so we had 23 participants, young participants, who fell asleep, who were tested from around 9:30 till midnight, and we had a 64-channel system. And so I'll tell you about what we found. But before that, I'll tell you what stages of sleep each person was in. So we had 10 people who were awake. And so what that means is that at the end of that 90-minute period, when the movie was presented, these participants woke up. So they had no sign that they were asleep. So and each stage of sleep was identified and registered by a polysomnographer. And so we had one person in N1, 3 in N2, 1 in N3, and then 8 people in deep sleep, 4 in stage 4 sleep, which is very deep sleep, and 4 in REM sleep. And so the question is, how can we probe for conscious processing of this movie at different stages of sleep? And the answer is to use intersubject correlations using the correlated component analysis that Jeff talked about. I won't go into too much detail, but the reason why, and so of course there's going to be a number of different ways that we could probe conscious processing in these different stages of sleep. But the reason we chose this is because these components, and this is results from a previous paper from Parr's group, and they find that these components are sensitive to engagement to the thing that they're doing, including movie watching, and these components fluctuate with fluctuations in attention. And so we thought this would be a good way to probe how much individuals at different stages of sleep are processing the movie, much the way you and I would process this movie, and much the same way that we probe patients to see whether or not their experiences are shared the way we would share different experiences. And so again, very briefly, we get 64 EEG channels, we can concatenate those, we run the principal component analysis, we extract a series of components that are maximally correlated across all the data, including all the people. Together, we back project this into an individual space, and then we can correlate the time courses of each of those components. So first, I'll show you global interceptor correlation. Again, Jeff talked about this. So this is correlating, or how similar the entire time course of the EEG activity is for, in this case, awake participants. And what we see here is a component that not only looks very similar to the component that Jeff showed with the taken data, but also very similar to the component that's produced by a number of papers by the para group. And so Jeff focused on the top component. I will eventually as well, but here I'm showing you the top 3 components. And these are what the top 3 components look like in sleep. So what's different about this from the patient group is that we can see how these components vary, or how similar they are to the awake group. So what we can do is we can correlate the time series of each of those components to each other to identify which components are most similar to each other. And so what we find is that components in awake, component 1 with component 2 is very similar between awake and sleep, and component 2 in awake and component 3 in sleep are very similar. So what this suggests is that there's some evidence that if you take the top component in awake as the component that reflects neural engagement, or the degree to which you're experiencing the movie, there's remnants of this component in different components in sleep, but it manifests in slightly different ways. Again, we can look at this much the same way we can look at the patient data, and we can see that we get interceptor correlations in and around 0.2 to 0.3, and this is completely in line with the data that Jeff presented. And we can see the similar results for the sleep data. I think the one thing to extract from this is that you get much neater clustering, or more people are more similar, or people are more similar in the awake state across the 3 components than they are in the sleep state. And so this is already interesting and informative to suggest that that even while asleep, just globally across the different sleep stages, there is some evidence that people are processing the movie to some degree. But what's really interesting is we want to be able to say, how much are each of these individuals processing the movie like the awake group? And so to do that, we can then take each person who's in a different sleep stage and run the exact same analysis with the awake group. And so before I show you the results, here's a prediction that I had, given what we know about the sorts of processing that are present at different stages of sleep. So we know that in middle stages of sleep, N2, N3, N4, that you get disrupted auditory processing, you get a breakdown of the propagation of auditory processing to later stages, whereas frontal parietal areas, there's an increase in activity during REM sleep. And again, Sid Coudier's work showed that you get this enhancement of memory during REM. So it could be that when you're in stage 1 and in REM, you're processing much more of the movie than you are at middle levels of sleep. And so the results don't line up with that perfectly, but I think what's important and what we can get from this is generally you see a negative trend for sleep state and intersubject correlation. So the shallower your sleep, the more information you're processing. But that's not true for everyone. So this is a person in stage 4 sleep, this is someone who's in deep sleep, and they're not very correlated to their group. This is someone who's in stage 1 sleep. This person is yet to go into deep sleep, is very drowsy, and they look very much like the group. But this person who's in REM sleep also looks like the group to the same degree that this person who's at stage 1 sleep. So here's some concluding thoughts, and in the spirit of the workshop, these aren't strong conclusions. These are meant to provide food for thought for us to discuss these results. But the idea is that we see some evidence that higher level processing of the movie during sleep. There's a general trend that the shallower your sleep, the more evidence that there is that you're processing the movie. But even for some people in REM, you're able to process, some people who are in REM are still processing the movie to some degree. Again, we can take this a step further, and this is one of the major strengths of using EEG and intersubject correlation, is that we're not tied to the entire time series. We can break this down, as Jeff discussed. We did the exact same analysis. We broke this down in a resolution of 2 seconds by a sliding window of 5 seconds, shifting every 3 seconds to get to identify peaks in the movie when people are most synchronized. And the idea then is we could relate this back to the specific stage of sleep that they're in. So globally what we find, and this is component 1 for awake, is that you get, so the numbers here are not as high as what Jeff found. So this is about between 15 or 20% of the time individuals are synchronized throughout the movie. One reason why the numbers are a bit lower is that these people were to some degree sleeping before the movie started. There's some degree of sleep inertia. They might be feeling a bit groggy. But this is component 2 of the sleep group, and this is about between 10 and 12%. Again, that's not a very high number, but 10 to 12% of a 5-minute movie is actually quite a bit of time. And I don't show it here, but component 1 of the sleep group has only 4 seconds where the entire group is synchronized. So again, this speaks to the fact that this component reflects some degree of processing of the movie. It just manifests in a slightly different way, which again isn't surprising because each participant is in a different state of sleep. Running a very similar analysis, we took just a number of participants. We did this for everybody. We identified the individual periods when each individual was most synchronized to the group. Again, this is taking each person who was asleep at different stage of sleep and correlating them to the awake group. And these are the different periods when they're most synchronized. And here we find there isn't as clear a relationship when you look at the temporal intersubject correlation. But what we do find again is a couple of participants who are in REM sleep who show a large portion of the movie, so upwards of 16% of the movie, so they're synchronized to the awake group about 16% of the time. Again, some more concluding thoughts. The idea here is that temporal ISC provides a different perspective on the shared experiences. Even though there's no clear relationship between sleep stage and the proportion of time the group is synchronized, there is evidence that, again, being in REM sleep more so than the intermediate stages of sleep, that there's processing of the movie. Again, this is in line with the workshop. This is very preliminary work, so preliminary that I haven't presented it yet. There's, I think, a number of things that we'd like to look at, and some of these things were touched upon earlier. So, for instance, what frequencies are driving these effects? If we break this down into different frequency bins, are certain frequencies driving the intersubject correlation more than others? What exactly is this component reflecting? So Jeff had showed some cool work on the results of the source analysis. But here we're showing that there are multiple components that seem to reflect higher level processing. What's the similarity exactly in terms of specific cognitive mechanisms that are driving those components? And one of the goals that I'd like to test at some point is, as we sleep, individuals fluctuate in different stages of sleep throughout a longer period than just 5 minutes. So often you fall asleep and you hear a noise and you wake up and you're suddenly aware of your surroundings, and then you also become immediately aware that you weren't a few seconds before that. And so a goal of mine is to link the specific time windows when people are synchronized to specific stages of sleep over longer periods. That concludes some of the work I've done on this. Just like to thank everyone who put this together in the Owen Lab. That's it.